Okay, I was cut off in the very last second or two. Battery died. And I was about to correct, I'd had a G here. This should obviously be a C times V3 because we need to get a C here and only this matrix has the 1 in the position of the C. So we have to add a CV3. So, again, we conclude the set B spans the set of 3x3 symmetric matrices, and you can't read the word matrices, but that's okay. Okay, now, can you prove that they're linearly independent? I have to do that over here. Okay, so is this basis linearly independent? Well, let me write it over here because otherwise it's going to look like it came here. Linear independence C1, V1, etc. equals 0 if and only if C1 equals C2 equals 0, and it's not n, it's, in this case it would be 6. Okay, so, well, I'm just going to say that if I add the C1 V1 through the C6 V6, what do I get? I get the matrix C1, because C1 times V1 puts a C1 here. C2 times the second vector gives me a C2 here. C3 times this one. C4 times this one puts C4 here. C5 times this one gives us my C5s here. And C6 times this matrix gives me a C6 here and a C6 here. Okay, well, let's see. What does it take to make all that 0? There's the condition. If the only way to get 0 is for all the C's to be 0, then we're linearly independent. Well, I'll leave it to you to think, does this assure that all the C1 through C6 are 0? If it does, we've fulfilled this condition for linear independence. And of course, we also have to verify that if I multiply, if all the C's are 0, we do get 0, but that's trivial and obvious.